In this video, we will introduce how to write the backpropagation or the derivative of the matrix operation. So actually, we will using this document to explain the detail. Okay, so if we suppose that we have a function which z of f is the input y, x, and y, and you will produce the z. So we will have x, y here, and we will produce the z. And the f could be an arbitrary functions which take the x, y, and y as the input and output another matrix z. Okay, so this is very generic form, and by using this form, we can calculate the z from the x, y, and so that when we have the gradient of the partial z over partial L, so we need to know how to calculate the partial x of partial L and the partial y over partial L, and by using this function. Okay, so this looks very complex since the all the things there is a matrix. But actually, what we need to do is just calculate the partial x of partial z and partial y of partial z, so that we can use in the chain rule to calculate. For example, if we want to calculate the partial x or partial L, we can use in the chain rule here to insert the z into the partial and the partial x or partial z. Okay, so since this is known, because this has been calculated by the backpropagation, so the only thing we need to calculate is the partial x and the partial z, and perform a matrix multiplication to get the partial x or partial L. Okay, so from the definition of the matrix derivative, the partial x of partial z, the dimension of partial x or partial z is actually the dsns, which is the dimension of the x, and the dz of nz, which is the dimension of the z. So it could be make a form like this. Okay, but this is still a very complex the formula. So let's start from some simple one, so that we can know how to we can calculate the derivative of a arbitrary function here. Okay, so let's check the first case. That's the most simple case here. Okay, we have x and y and z. Instead of a matrix, it's just a vector. So x is a vector whose dimension is dx, y is a vector whose dimension is dy, and z is a vector whose dimension is dz. Okay, so we have the function of x, y will be equal to z. So that's what we want to do here. And suppose that the gradient of partial L over partial z is available, which has been decided by the backpropagation procedure. So now we want to send this using this gradient to calculate the partial x of partial L and the partial y of partial L. Okay, so how we can do that? As we said before, the only thing we need to calculate is actually the partial x of partial L will be equal to the partial z of partial L dot partial x over partial z. So the only thing we need to do is that we need to calculate the Jacobian function, partial z over partial x, so that we can use the Jacobian function, multiply the Jacobian function with the gradient of the z, so that we can get the gradient of the variable x. Okay, so we can, so the only thing we need to do is that we need to get the Jacobian matrix here. So we can use in the redo as an example. So in the redo function, the function x will be the max of 0 and x, since the redo function is something like this. Okay, so the function will be, if it's less than 0, it will be 0. If larger than 0, it will be x. So the redo will look like this. So for example, if the input is 1, minus 2, 3, minus 1, so all the minus will become 0, and all the positive number will keep the same. So this is the redo function. So for example, if the gradient is 4, minus 1, 5, 9, and the input is 1, minus 2, 3, minus 1. Okay, so in this case, we can calculate the Jacobian function. And we can check that actually the Jacobian function is that we need to calculate the partial xi of partial yj here. So we can check what's the partial xi or partial yj, because the value of the value of yj is actually equal to xi if xi larger than 0. Okay, if xi is larger than 0, and if xi smaller than 0 or equal than 0, yi will be 0. Okay, so it means that when we partial xi or partial yi, so for example, we just take a partial xi here and the partial this one. So we can see that the only non-zero item is the xi whose value is larger than 0. Okay, so maybe you can check the first line. The first line, this is 1. So the first the x11 is 1. For others is 0. Because in this case, the I this should be j here. Okay, so if I and j is equal, it will be 1. For others is 0. So for the first line is 1 and 0. For the second one, since it's minus, so it's this one. So there's no xi here. So everything, all the item is 0. So we can follow this rule. The third one, for the third one, the x3 is 1. For others is 0. And for this item, since it's negative, so all the items are 0. So all the derivatives are 0 as well. So in this way, we can write down the Jacobian matrix of the redo function. And then the next thing we need to do is simply multiply the Jacobian function with the dl over dy. So since that, when we want to do the calculate the partial L over partial X, we actually can use a partial Z or partial L and a dot partial X or partial Z. So the partial X of the for here is not Y, is not Z, is Y here. So let's modify it. Okay, so this is Y. Okay, so for this item is the Jacobian function here. Sorry, this is not true. For this is Jacobian function here. And this item is the upstream gradient, which is this one. So we just multiply the Jacobian function with this one so that we can get the value of partial X or partial Z. Okay. So this is one way we can calculate the gradient for the redo function. However, typically we will not do that. Since from this Jacobian function, we can find that most of the items are 0. So if we write down the Jacobian matrix and using Jacobian matrix to do the multiplication of the upstream gradient, actually most we for this one we need to do the 16 multiplication. So the first line, this one, so this is we need to do 16 of the number multiplication here in order to get the final answer. But actually, most of the items are 0. Actually, only 2 of the elements are non-zero. For others are 0. So actually, we only need to do 2 multiplication instead of 16 multiplication in order to calculate the derivative of the redo function. So the other way is that we're just using this formula, and so we only need to pick up the non-zero item to calculate the redo function. So by using this formula, the gradient we can follow the gradient in this way. If the x here, for the x1 is positive, so we just send the value to here directly. And for the x2 is -2, so we just ignore the upstream gradient, just set this value as a 0. So we can do the same thing for the third item is positive, so we send the 5 to 5 here. And the -1 is negative, so we just set the value as a 0 and ignore the gradient here. So by using this way, we only need to do we don't really need to do any modification. We just check the value of the input tensor x, and use this to decide it. If the x is 0, it is larger than 0, we just send the gradient. If it's less or equal to 0, and we set the gradient as a 0. So by using this way, there's no multiplication. We just do some positive positive check and to decide if we want to allow the gradient pass or not. So the complexity of this algorithm is much less than the Jacobian matrix. Okay, so but if we have know how to do that, do the backpropagation for the vector, how about the matrix? if the input x and both input x and y are matrix, and the z is a matrix as well. Okay, so we can the same as a vector, we can have a upstream gradient here for the partial L or partial Z. And then in order to calculate the partial L or partial X, we need to have a Jacobian matrix here, the partial Z of partial X, so that we can write down this one as the partial Z of partial L dot partial X of partial Z. Okay, so we need to calculate the Jacobian matrix here. So we can look at this picture. We know that the partial L or partial X can be calculated by using a matrix multiplication of the partial L or partial Z and the partial Z over partial X. So this is a upstream gradient, and this is a Jacobian matrix. Okay, so let's check the simplest example. If the function f is actually the y equal to xw. So for example, if x is a matrix of 2 by 3 and w is a matrix of 3 by 4, and the result will be, so this is 2 by 3 and this is 3 by 4. So the output is cancel this 2, this is 2 by 4. So this is a matrix multiplication. So by using the formula, we can write, actually we can write the y of the by using the x and w by using this formula. That's the definition of matrix multiplication. Okay, and so for now we want to calculate the gradient against the x here, and we know that the dimension of x is n by d, so the gradient, the dl over dx, will be n by d as well. This is by definition. So, but the problem is that how we can calculate this matrix. Okay, so by using the Jacobian matrix, we know that the Jacobian matrix will look like this. So the ds and dy will be this dimension, and the dy or dw will be this dimension. So let's focus on dx over dy here. So that we want to calculate the derivative of L against the variable x. So how could we calculate this? So let's do it one by one. For the first entry, which is the dx11, the dl over dx11. So this one will be we can use the chain rule to write this down. And the first item, the dy over dx11, it should be, we can try to calculate this one. So for the first item in this matrix, this will be a 2 by 4 matrix. Since the x11 is a scalar, but dy is a 2 by 4 matrix, so that the result of this one, the result of this item will be 2 by 4 here. Okay, so let's try to calculate the first item entry in this array, the dy11 over dx11, and we can write down the formula like this. The y11 will be y11. It means that the n is 1, n is 1. So the y11 will be the d and the n is 1. So it's x1d and the n is 1 as well. So this is wd1. Okay. So this explain it. You will become this formula. And let's go it up. And if we know that the formula of y11 is like this, so let's do the partial x11 over partial y11. So we will actually take the derivative of this formula, and it seems that the only item here, we have 3 items here. The only item with the x11 is the first item. So for this 2, you will be 0. Then for this one, you will become the w11. Okay, so we know that this item with the dy over dx11 is actually the number here. Actually, the number here, and we can continue to do a similar thing, and then we can get this one. So the first line of this matrix actually the w here. So the dy over dx11 will actually the value of this the matrix is actually copy from the w here. Okay. So we can continue to do all the jobs. For this one, this is y21. So we can write this down here. And none of the entry here has the x11 inside. So that the gradient of the d11 over d the 21 will be 0. So actually all the value in the second row will be 0 because we are directly over x11. Okay. And for this one and this one, so we can just do a dot product between them. So the dl over dx11, we can see that this is actually a scalar because L is a scalar and the x11 is a scalar as well. So the derivative should be a scalar, and it will be actually the dot product between these two matrices, between this matrix and then this matrix. Okay. So you need to notice that even though we write it as a matrix, but in the derivative, it's actually a vector. So we just flatten the matrix into a one-dimensional vector. So that the dot here will become an inner product. So we just do the inner product between these two matrices. So by using these two matrices, we can get the first entry of the dl over dx will actually a 0. And then we can continue to do the same thing for every entries, so that we can get all the 6 number here. Okay. So maybe we can try to do we can try to calculate some of them. For example, the zeros, the dx. Let me try to do this. The dx 12 of the dl. Okay, so in this case, the j will be 2, so we will choose the second line here, and the I will be 1. So this is the first row here. So we just make the inner product between these two matrices. So 2, 2 is 4, and 1, 3 is 3. 3, 3, 3, this is minus 9, and the 2, 9 is 18. Okay, so the value will be the 7, the 25 minus 9, so it will be 16. So it will be 16 here. Okay, so we can do the same thing for others in the row. So you can say that when we do the same thing, we can just get the two vectors and make the inner product of them, so we can get the answer. And actually, if we write down everything together, so that you can see that for every calculation here, we are actually select one of the column from the W and one of the column from the dl over dy, which is the upstream gradient. So one column here and one row here and one row here. So this actually is we can write this down by using the matrix multiplication. But in the matrix multiplication, we actually get one of the column and one of the row. So actually we can write this formula in this form. So we just take one of the columns from one of row from this here, and we can get one of row here. But in order to write it as a matrix form, we need to get a transpose of a W. So that get one of row will be get one of a column. So that we just get one of the row from the dy over dl and one of column from the W. So we can write you can write the formula in this way. So actually this we can write the formula by using the dimension only, because we know that the dw over dl, the dimension of dw over dl is the dimension of the x, so that is n by d, and the dl over dy is the dimension of the y, so which is the n by n here. So in order to make this formula, because we know that the y is equal to xw, and we want to calculate the dx over dy. So this is dx over dy here. So it's dx over d this one. Okay, so we know that the answer must be the multiplication must be the w here. Okay, so but the problem is that we need to make sure the dimension is correct. Actually, by using the matrix derivatives, we know that the answer for this one will be the W transpose. But without using this formula, actually we can just check the dimension of a variable to decide if we need to put the transpose or not, because this is n by d, this is n by n. So the only way we can produce the n by d from the n by n is that we need to have some matrix which is n by d, so that we can cancel those two and get the n by d here. Okay, so what's the matrix with the n by d dimension? We know that the W is d by n, so the transpose will make it to be the n by d. So in this way, we can know that we need to have some transpose here. Okay, so the necessity of the transpose can be decided by two ways. First, we can just like the procedure above here to write down the formula of the W and the dl dy here, and then we know that we need a transpose, so to match the inner product become a matrix multiplication. But actually we can just use the dimension check to decide if we need the transpose or not. Okay, so this is actually the multiplication. So we can using this to implement the backpropagation for the matrix multiplication in the neural network, and this can be used to implement the fully connection layer of the neural networks, and the CNN can be implemented by using the matrix multiplication as well. We will introduce the implementation of a CNN by using a large matrix multiplication later. But for now, we have know that how we can write the backward function of the matrix application here. The only thing we need to know that we just multiply the upstream gradient by using the other variable. For example, if we want to calculate the dx or dl, we just multiply it by the w, and we can do the same thing to calculate the dw over dl as well. Okay, so maybe you can try to see what's the formula should be here. And we know that this is dy over dl, so we will do this, and d w over dy. Okay, and so for this one, we can use a dynamic dimension check to see how we should write this formula, because we know that this must be something related to x. So the only thing we need to do is that we need to make sure the dimension is correct. So for example, for the dw of dl, w is d by n, and then this is the dl of dy is n by n. So that in order to have this, we need to have some matrix which is d by n here, and then the n by n. So we can cancel this two to get the d by n. So the x, so it means that the n by n, the gradient should be, we need to swap this two, so that it should be the dy over dl here, and we erase this one. So this should be like this, and we need to have a matrix which is d by n. which is d by n here. So this will be the x transpose dot dy over dl. Okay, so we know that we need a transpose here for the x as well. Okay, so that's all for the directive of a matrix function.